All right, let's get into it. Behind pretty much every click, tap, and swipe we make, there's this invisible battle for efficiency going on. Today, we're going to pull back the curtain on one of the real unsung heroes of that fight, an algorithm that's basically a production line for logic itself. So, if you've ever dabbled in digital logic, you've probably met the Carnot map. And it's great. It's this fantastic visual tool that lets you simplify logic almost by instinct. But here's the catch. It has a huge weakness. It's built for our brains, not for computers. And when problems get just a little bit complex, our intuition totally falls apart. And that's exactly where Quine McCluskey steps in. It's the systematic, heavy-duty approach that's built for machines. So, here's our game plan. We'll start by seeing exactly where these visual methods hit a wall. Then, we'll bring in the Quine-McCluskey algorithm and break it down into its two main phases. First, finding all the essential logic pieces, and then picking the best ones to build the most efficient solution. And finally, we'll see how this whole process has a massive impact on the tech we all use. Okay, first up, the visual limit. Let's start with the core problem. Why did we even need a new way of doing things? The breaking point for K-maps is actually surprisingly low. The magic number is 5. The second you hit 5 or more variables in your logic function, the whole visual thing just becomes a mess. And trying to do 6 variables? Forget about it. It's pretty much impossible for a person to manage. And that really gets to the heart of the issue with these visual methods. The problem stops being about logic and turns into this crazy spatial reasoning puzzle. It becomes incredibly easy to miss a simplification or just make a flat-out mistake. We clearly needed a system that didn't depend on our eyes at all. And that is exactly what Willard Quine and Edward McCluskey gave us. They created a method designed from the ground up to be run by a machine. The Quine-McCluskey algorithm is all about being systematic. It's a tabular method, which is just a fancy way of saying it works with lists and tables instead of visual maps. It follows a very strict, step-by-step set of rules, which is perfect for a computer that needs crystal clear instructions, no guesswork allowed. I think this is the perfect way to picture the difference. Using a K-map is kind of like being an artist, carefully sculpting a solution based on skill and intuition. But Quine-McCluskey? Oh, that's a full-on industrial production line. It takes in the raw logic, runs it through this standardized process, and just systematically chips away every single redundant piece until you're left with the guaranteed smallest, most efficient result. It's not about art. It's about pure, repeatable manufacturing. So how does this production line actually work? Well, it all kicks off with phase 1, finding every single possible simplified component. The goal here is really straightforward, but it's also incredibly powerful. The algorithm's entire job in this phase is to find all the prime implicants. Just think of these as the simplest possible building blocks for our function, kind of like the basic Lego bricks we're going to use to build our final circuit. So, how does it find these little Lego bricks? It's actually a pretty brilliant process. First, it just lists out every input that gives you a 1 or a true output. Then it gets organized, grouping all those terms based on how many 1s are in their binary code. Now, here comes the magic. It starts methodically comparing terms in neighboring groups. If it finds 2 terms that differ by just 1 single bit, bam! It combines them into a new, simpler term, replacing that differing bit with a dash, which basically means we don't care about this bit. It just keeps doing this. Combine, simplify, repeat, over and over until there's nothing left to combine. And the terms that are left standing, those are our prime implicants. So the main thing to take away from phase 1 is this. We now have a complete catalog of every possible simplified piece for our logic function. The algorithm has done the heavy lifting and found all the building blocks we could possibly need. Okay, we've got our box full of building blocks. Now it's time for phase 2, which is all about selection. Which of these blocks do we actually need to build the leanest, meanest final structure? The name of the game in this phase is minimalism. The whole goal is to pick the absolute smallest set of those prime implicants we found to cover every single true case from our original function. No redundancy, no waste, just peak efficiency. To do this, the algorithm uses a special tool called a prime implicant chart. It might look a little intimidating, but it's actually pretty simple. The rows are all those building blocks, the prime implicants we found. The columns are the original, true outputs we need to cover. And that X, it just means, hey, this row can take care of this column. So the puzzle becomes, how do we pick the fewest number of rows to make sure every single column has at least one X in it? Well, the algorithm starts with the no-brainers. It looks for what are called essential prime implicants. It just scans down each column of the chart. If it finds a column with only a single X in it, well, that's a dead giveaway. It means there is only one prime implicant in our entire list that can cover that specific output. So that implicant isn't just an option, it's essential. It absolutely has to be in our final solution. The whole selection process is just elegantly logical. First, you pick all of those essential prime implicants. Those are your non-negotiables. Then you see what's left. If there are still any outputs that need to be covered, the algorithm strategically picks the absolute minimum number of other implicants to finish the job. The result? You get the guaranteed, mathematically proven, simplest possible expression for your function. No maybes, no good enoughs, the best solution, period. So, we have our minimal solution. But why does this whole thing have such a huge real-world impact? Because this systematic approach completely unlocked the door to automating digital design. So why is this algorithm such a massive deal? For starters, it guarantees the best solution every time, and it completely removes human error from the equation. And here's the real payoff. A simpler logic expression directly translates to a circuit with fewer components, and that means smaller, faster, and more power-efficient chips. This is exactly why the principles of Quine-McCluskey are basically the engine running inside the modern computer-aided design, or CAD tools, that engineers use to design the microchips that power our entire world. It's also helpful to understand the specific job this algorithm has. You might have heard of other famous logic algorithms, like SAT solvers. Their goal is to answer a yes or no question. Does a solution for this problem even exist? But Quine-McCluskey asks a totally different question. It comes in and says, okay, we know a solution exists. Now, what is the absolute most efficient way to build it? Its whole purpose in life is minimization. And that leaves us with a really fascinating thought to end on. The Quine-McCluskey algorithm is this powerful, elegant process that just works tirelessly behind the scenes. And it makes you wonder, right? How many other invisible, systematic engines just like this one are quietly running our world, turning mind-boggling complexity into the streamlined efficiency we all take for granted every single day?